Okay, guys, this is going to be number 2 on the Chapter 16 review. We're going to be talking about the concept of Lewis acids and bases. Now, I'm recording this video ahead of the lectures that you're going to be doing on this topic, and I already know, based off many semesters of tutoring this, that this is going to be a concept that a lot of you struggle with. And that's mainly because I feel that there are some things that are prerequisite knowledge about Lewis structures that perhaps some of you aren't familiar with or you've forgotten. So what I'm going to do for this problem is first do a really quick little preface on like how you approach these problems, okay? Because hopefully you're watching this video after you've already seen the material and you're like, I don't understand this. So then that's what this is for, okay? All right. So this question is asking us about to identify the Lewis acids and bases in the following reactions. Okay, so a Lewis acid. Now let's contrast that. So in the previous video in this playlist, we talked about the concept of Bronsted-Lowry acids and bases. Okay, so with Bronsted-Lowry, we said that acids were proton donors and bases were proton acceptors. And we looked at the chemical equations and we said, okay, well, if it's gaining a proton, we'll call it an acid, and so on and so forth. We use the equation to identify the acids and bases. Now, this is a much different process on how you identify Lewis acids and bases, and unfortunately, for a lot of folks later on in life, you're going to be using this definition pretty much more than anything else. But what it does is it requires a knowledge of Lewis structures. So these are called Lewis acids and bases, and this is the same Lewis of Lewis structures that you learned in Chem 101. So it would make sense that his definition requires the use of Lewis structures to identify acids and bases. So that's my first tip, okay? Tip number 1. If you can't identify, acid or base, you need to draw your Lewis structure. Some of these are pretty apparent based off some other tips I'll teach you later. But that help with identifying these. But the tip really, at the end of the day, the best way to figure out which is a Lewis acid or base is to draw the Lewis structure out. And then it becomes readily apparent what will be acting as an acid and what will be acting as a base. But let's actually get into it really quick. So you probably saw in class that we call a Lewis acid. It's a very different definition because a Lewis acid is it's an electron pair. It's an electron pair acceptor. We'll call it a lone pair acceptor or electron pair acceptor. Okay, so this is very different. It's a very different concept. Okay, so Lewis acids and bases, they care about electron pairs, and in previous, for example, what do I mean by that? I mean like with water, for example, there are lone pairs, right? And each of these guys we would call an electron pair. So basically, if a molecule were to accept those lone pairs or electron pairs, then they would be acting as a Lewis acid. And we're going to do some examples where we see that. By contrast, we say that a Lewis base is an electron pair donor. Okay. So already off the bat, we open ourselves up for immediate confusion because Lewis acids are electron pair acceptors. But if we look back up to the Bronsted-Lowry definition, we use this terminology that they're proton donors, right? So just I want to make this point really clear, that proton donors are very different than electron pair acceptors, okay? Protons and electrons are entirely different things, okay? So you need to separate these two concepts in your mind. Turns out that the Lewis acid-base definition is so general that it actually will accommodate the Bronsted-Lowry definition. is the best definition for a Lewis for bases and acids actually. So if you always use Lewis, it's not always very practical, but if you use Lewis acid-base definitions, you always determine what's the right acid base. You can always identify it easier. Okay. You'll get better at that as you go further in chemistry. I think when I took this class, I didn't really understand it to the same level I do now. So don't be too frustrated if it's something that doesn't make complete sense. Okay. So we have our concept of Lewis acids and bases. Lewis acids are electron pair acceptors, and Lewis bases are electron pair donors. Okay. All right, so let's take a look. So then we said, I have another tip for you. Tip number 2. We'll say incomplete octets are usually Lewis acids. Okay. Incomplete octets are usually Lewis acids. What do I mean by that? So, like, for example, we said that, this ends up being brought up later. So BF3, I'm going to draw that out of here. It's boron trifluoride. It would be a trigonoplanar molecule, right? It exists in a plane, right? And if remember, there's this concept of formal charges that we learned about. Formal charges in Chem 101. And the way you computed that was the valence electrons minus the number of bonds plus the number of lone electrons. Right? So hopefully you remember that. So then if we did the formal charge for this, boron has 3 valence electrons minus the sum of the number of bonds. There's 3 bonds here. And we could say there's no lone pairs. So we could see that it has a formal charge of 0. And it's weird because this boron doesn't have a complete octet. So this is a stable compound without having a complete octet. This was one of those like canonical examples that we went over in 101. And what that means is that there are empty orbitals that can accept electrons. And that's what we mean by an electron pair acceptor. So, if we had a water molecule, who had its lone pairs, well, those lone pairs could be donated to fill those empty orbitals that we're talking about, okay? So you could see then here that the water is donating its electron pair to fill those orbitals. So that means it's acting as a Lewis base, right? We said that Lewis bases are electron pair donors. So that's what water's doing here. It's acting as a lone pair donor or electron pair donor. And boron has these empty orbitals that can readily accept electron pairs, which is why it's acting as a Lewis acid. Okay? So this is just an example. Don't worry about having to know this all the time. Don't have to worry about the definition necessarily perfectly, but it is discussed in your notes. But what I'm trying to bring up is the fact that incomplete octets, like this boron structure here, have empty orbitals that can be filled by electron pair donors. Okay? Which is why I said they act usually as Lewis acids. So look for incomplete octets. Those are usually your Lewis acids. Okay? And then tip, by the same kind of idea, tip number 3, high cationic charged metals. What do I mean by that? Highly positively charged, yep. Are Lewis acids also. So if you look for highly charged metals, they are typically Lewis acids also. So we can use these tips to figure out which are Lewis acids in. Right, these are. Okay, so be on the lookout for highly charged metals, okay? And be on the lookout for incomplete octets. These are usually going to lead you in the direction of a Lewis acid. Okay. On the flip side, last tip. Negatively charged molecules are usually, I'll give it some more space, Lewis bases. Okay? So negatively charged, remember, usually if you're negatively charged, that typically means that you have more electrons than you would normally, right? That's what it means to be like an anion, to be negatively charged. And because you have more electrons than you normally do, you can donate those more readily because you want to alleviate that negative charge. Okay, we'll see examples of all of these in the upcoming problem. So hopefully that makes sense. These are just some tips that I've encountered that help me get through problems like this, okay? So be on the lookout for incomplete octets. Those are Lewis acids. Be on the lookout for highly charged metals. Those are also Lewis acids. And then if you see a negatively charged molecule, it's usually going to be a Lewis base, okay? All right, so give me just a second. At a technical difficulty, so there might be a cut right there. Okay, so let's go into the first problem here, and we're going to identify the Lewis acids and bases. Hopefully we can use the tips, and that will help us get through these problems. Okay, so with part A, we see FeClO4, 3, and 6 water molecules, okay? And we have ClO4 minus on that side. Okay, so we see here that FeClO4, if we were to look at this, this here is a ionic compound. Ionic compound, right? It's a metal and a non-metal. It's a polyatomic ClO4. That's perchlorate. And we see that each ClO4 from Chem 101 we know is a -1 charge, a perchlorate, which would mean, since there's 3 of them, that would accumulate, if there's 3 of them, that would accumulate a charge of 3 minus. Therefore, it would mean that in order to stabilize this ionic compound, then the iron here would have to be a charge of 3 plus. And then that's kind of how I would identify the fact. Well, we said Fe3 plus. Well, that would kind of work with tip number 3 in this case. A highly cationic charged metal is typically going to be a Lewis acid. So that would allow me to identify that this is my Lewis acid. Okay, that's what I meant by highly charged cationic metals. Okay, now like, what's the chart? What's the Lewis structure for water? Well, it would just be what we draw before. It was the bent structure here. And we can see that it has readily available lone pairs or electron pairs that it can donate, okay? So electron pairs to donate. Okay? So that's what we mean by a Lewis acid, because it has it's going to get attacked. It's going to be accepting lone pairs, okay? So like I said before, be on the lookout for highly charged metals. That will be able to identify what are Lewis acids, okay? And if you were to actually draw the structure of FeClO4, I'm going to erase it after, but it would be Fe. We can see that it's making 3 bonds, so ClO4. I'm not drawing the ClO4 because it's a kind of a big structure. That'd be ClO4, right? You see that it's making 3 bonds, so it has an incomplete octet, so then it has these available orbitals where electrons can be pushed in, okay? Awesome. So that's what I meant by highly charged metals are typically going to be acting as Lewis acids. So that means the water in this case, this got messy real quick, the water is acting as a Lewis base. Okay? So, be on the lookout for highly charged metals. Let's keep going. Part B. CH3N. Oh, and then we saw that BF3 again. Remember, that structure of BF3, it has that incomplete octet, which allows it to act as a Lewis acid. Right? And if that's the Lewis acid, then we could say that this molecule here is acting as a Lewis base. Okay. And then finally, I'm gonna have to, I could just write, I'll erase this stuff really quick. Okay. Let's take a look. Well, we have this HIO and NH2. So let's draw the structure of HIO. We have a total of, that's 6 plus 7 plus another 1. That's 14 valence electrons. So that would be HOI, like that. Doing my complete octets, we could see that that would add up to a total of 14 electrons. That's 2, 4, 6, 8, 10, 12, and 14 with all those bonds, adding up to the 14 valence electrons. And we have NH2, just drawing a basic structure of NH2. It's an NH2 minus, so normally there'd be 5 plus 2 electrons, that'd be 7 valence, but we have this extra one, so it's going to be a total of 8 valence electrons. That's 2, 4. I need to add another lone pair here, and then it's going to be a minus charge. So like I was saying before, we said that negatively charged molecules typically act as Lewis bases. So this guy here is negatively charged. This is going to be our Lewis base, which would mean then, since this guy is accepting electron density, that's going to be a Lewis acid. Alrighty, that's how we're able to identify this. Okay, so I know that's kind of a big concept. It's a little bit hard to identify, but if you stick to these tips, I think at least in this class, you'll be able to go and answer pretty much most problems with respect to Lewis acids and bases. I will say that this topic is a very deep topic that will be discussed really heavily in organic chemistry. So for those of you who are super interested, you can always come to me and I'll explain it even further. But for the purposes of our class, this is probably enough to allow us. You should be able to identify you should be able to visually tell me which is acting as a Lewis base and acid. Okay, sometimes it's not always readily apparent. You know, just think about what you knew before the video and after. So now you can identify many more molecules as acids and bases, even though there may not be H plus that's produced in the solution. Okay, so hopefully that was helpful. Remember to use these tips to help you solve problems like this. Okay, see you in the next video.